Here for Professor Lu's class, 264, right? Good. So as you may know, Professor Lu is in jury selection. He hoped that he would be ready, but he has sent me an email saying it took longer than he thought. I guess he wasn't able to get out of it. We'll see. So I'm here to teach today's class. I teach the other class. And the two sections are actually exactly in sync. So this is what I taught my students yesterday. Last week was recursion, and I think Professor Lu told you how important this is. This is a topic that basically will figure into every assignment of the rest of the course, and every exam, you can be assured of that, will have recursion. This week we're going to talk about the remaining learning outcome of the course. So if recursion is one of them, we've looked at files and data management for structures so far. This week is the fourth one, which is on dynamic data structures. More specifically, it's going to be lists, or linked lists. So, by the way, I'm Professor Elm. So the topic today is linked lists. It's the simplest of dynamic data structures that we'll talk about. Later on in the course, we'll talk about binary trees and some more advanced things building on top of this. Linked lists is the starting point, and it's a very good introduction to how real data structures are constructed. So imagine for a moment that we're building a text editor. And the text, I'm sorry, hopefully you can you see that over here? Oh, I'm sorry about that. Okay. Because I don't dare. Does Professor Lu use the document? Oh, okay. Well, maybe I can do that. Anyway, I think I'll be fine with this. I'm only there for the day. So let's see. So let's imagine you're building a text editor. And text editors, as you know, it's not just like reading a file once and you're done. You've done that already in the cat or the echo and similar assignments. But if you're doing a text editor, you're going to have to read a file from disk and keep it in memory. Because of course you're going to have to show that text to the user, and the user should be able to edit. So for example, things that a user might do, you might go in and change parts of a line. So if this is your file, you're going to have variable sized lines. And a user might end up inserting lines too. Let's say I wanted to add something here, and I'm editing text. The user of my text editor obviously don't want to know how this is stored. They want to use the editor as they are used to Microsoft Word or Star Office or whatever. So if we want to achieve this, we need a data structure that can keep track of the lines, the individual lines, as well as the collection of lines in the entire file. We can't just have them. We can't just have them on the disk. We have to keep them in memory. And the problem here, of course, is that this is a resizable data structure, a resizable data object, because I might insert rows, I might delete rows. If we use an array, which is what we so far have basically taught you to use. Well, arrays are good in many ways, but the problem is they are not dynamically resizable. So if I have an array, let's say the way I would do this, if I was doing an array, I'd have a double sharp pointer. Right? Every line would be a string. Maybe it is allocated whatever. If we have 20 characters, we would have 20 characters on the line. We would have 21 characters. One for the contents of the string plus the terminating character. And then we would have another start to say we have a list of them. We have an array of character pointers. But of course, this is not dynamically resizable. So if my user, for some reason, adds a line in the middle here, I can't resize this easily. I can't fix this easily. What we end up doing is creating a new copy that is maybe, instead of 5, 6. So I would probably do something like this. If this is my data, I would show you how I would allocate this to start with. Malloc, and I have 5 rows to start with, times size of char pointer. Because of course I'm allocating pointer space. But as I said, I insert a line, I'm going to have to change this to a 6. Typically that means creating a new piece of memory that's now 6 slots big, copying over the things that are in the old memory and deallocating the old memory. That's a problem. The other problem is, if I want to insert something, and I would say difficult to insert and remove anywhere, let's see, anywhere except beginning, end, I should say. What I mean by that is if I'm inserting this stupid line in the middle here, even if I have space, let's say I planned ahead and I allocated 10 slots here. So there are 10 slots for additional lines to be added. If I want to insert this line right here, obviously I'm going to have to copy this one here, one step down, this one there, and this one there, and then I can insert this. It's not, a list like this is not designed for insertion. I can put things at the end, that's easy. But I can't put things easily in the middle. And especially the worst case is, of course, if you put something at the beginning, because then you're going to have to copy everything else. So are there any good things about arrays? It sounds like I'm dissing arrays totally here. But of course there are good things about arrays. Any thoughts? Yes?
Any bit of information in the array can be accessed randomly.
Exactly. So arrays have random access, which means if I have this data, I can say for any index, well, 4, for example, if I want to access this line, I can just use the square brackets operator, which is really data. It's really a memory offset. It just means this, on this location in memory is where the list begins. And I can access any of the other elements by just jumping a certain amount of steps in memory. So that's the good thing about arrays. And they are a low-level data structure that most programming languages support, C included, because of this. And remember, just to compare this, this is one of the reasons why files are slightly problematic. We don't have random access to a file. We open a file, we have a file pointer that starts at the beginning, and then we can do operations to advance, and we can play back and all that. But we can't just read at any location. If I want to read at any location in the file, I first have to jump to that location. Anyway, so if I'm building a text editor like this, it's clear to me that an array solution is not optimal because of the reasons I outlined here. So today we're going to look at linked lists which are slightly, which are very different and are not based on arrays at all, really. And the idea with a linked list is that instead of having this long piece of memory, this long chunk of memory that's contiguous, starts at one place and goes on for a certain amount of slots, we create these little elements that we call list nodes. So node is the word that I'm using. And each list node contains two things. It contains a payload, or whatever it's carrying, and it contains a next pointer. So the understanding here is that instead of having a chunk of memory, we're going to create individual pieces for every part of the list. Let's start with numbers. If I'm storing a number, well, the payload would be, let's say, 42. And the next pointer would point at the next, obviously, you can hear from the name, the next element in the list. Very simple. So you get this chain, this data structure, where one element is the springboard to the next element. And you can go on forever, of course, if you wanted, until you reach the end of the list. And typically you signify this. When I'm drawing it, I'll use a cross. What it really means is that this is null. Null means the next pointer of a list node is null. That means this is where the list ends. Okay. The beautiful thing about this is that we no longer have the constraint that the data we're storing has to come after each other in a contiguous piece of memory. Because all we have to say is that each element is going to occupy some piece of memory. I don't care where. Mr. Operating System, you can allocate it wherever you'd like. Because I'm going to keep track of the next element in the line in my data structure. So that means, even if conceptually speaking, it is a long list, starting at element 0 here, and going on to element 3, if you look at where this ends up in memory, it's probably going to be all over the place. You might be jumping back and forth in memory addresses without worrying about it, without caring about it. Okay, so this is a linked list. The start of a linked list is called or referred to as the head of the list, and the end, or I should actually point to the element itself, that is the last element is called the tail corresponding. So if I would look at my array and compare it to linked lists, I will get some differences. First of all, this type of data structure is eminently resizable. Because if I wanted to insert, let's say, 13 between 7 and 17, it's very easy. What I do, instead of reallocating and copying and all that business, I just point the pointers, I re-point the pointers to sort of include that. The element I'm inserting after its next pointer will now point to the element I'm inserting. The element I'm inserting will point to what used to be after the element, so in other words, the element I'm inserting before. So, dynamic resize, or it can shrink and grow, in other words. And this part here about things being difficult to insert, of course, is the opposite. Easy to insert and remove anywhere in the list. In the beginning, at the end, any point in between. I don't have to spend a lot of time copying whatever comes next in the list because I frankly don't care. They can stay wherever they are. We just make sure that we update our pointers, and we're going to maintain a list that is a sequence from beginning, from head to tail. But of course, if we look at this part, what about random access? Any thoughts here? I'm setting you up. It should be easy. Well, I'm not setting you up. I think I'm rolling out the red carpet here. Yes?
So you need to traverse through the linked list in order to find a certain element. You can't just jump to it.
Exactly, because I don't have the luxury of knowing, as I do with arrays, that the array starts here and it goes on until this location. I don't have that luxury. I can't just say, okay, I know the list starts here, so the next element is going to be counting forward, 10 bytes in the future. I don't know that. We gave up that freedom when we said we're not going to use arrays because they had too many problems. So if I want to access, let's say, 17, index 0, 1, 2, 3, well, I'm going to have to go through every element, starting with the first one, until I get there. Because I can't take any shortcuts. In order to get from 42 to 7, I have to go to 42 first. I have to go from 7 to 13, 42 to 13, I have to go through 7. 42 to 17, I have to go through 7, 13, and then get to 17. So that's the downside. There's no, let's say, sequential access is what I was saying. So my plan today is to talk about linked lists because it's a big part of the programming assignment that's due on Friday. And I assume that Professor Lu, unless he gets called in to actually serve in a jury, will be back on Thursday. And then I'll let him talk about the main part of the assignment, which is on merge sorting. And we'll talk about sorting algorithms and all that. I want to give you the weapons to not worry about the data structure. So a big part of the assignment is knowing linked lists, because that's what you will be sorting. You'll be sorting lines of text, or strings really, sort of like this text editor example. So if we were to start implementing this, that's my goal for today, to implement a linked list that's capable of inserting elements at the front or the end of the list, deleting elements, traversing the list, in other words, visiting each of the lines and printing them. That's my goal for today. So, let's see then. We're going to get started here a bit. Hopefully, is this too small for everyone? Can you read this? Fine? Okay. Let me know if you see errors or if you have questions. I wanted to create a simple, I'm not going to create a pure text editor because doing that would take a lot of time, of course, and you'd have to do things like being able to manipulate the cursor and draw text on the screen. But I'll do something simple where we read files, but instead of reading one line at a time, printing it, and then throwing away the memory, I want to store that memory. I store that line in memory so that I can do things with it later. And we'll build on that on Thursday to take those lines and actually sort them. So I'm going to need a few things here. And let's see, we're going to start with the main function, and I'll build from there, so make sure that you have space, maybe before or after, whatever you want to lay this out. I will be adding stuff here. Will come here. So if I am reading command lines, arguments, I'm going to make sure that I get a file name. And when I get a file name, I'll open that file for reading. Hopefully this is not anything weird for anyone here. If I'm not able to open the file, I'll use exit failure. So I now have an open file. I want to read from it. So I would create a buffer, probably, to store each line in the file I'm reading. I will just define a buffer size here. Oops. Okay. And we'll use our friend fgetS. So while fgetS buffer, let's see, buffer size, and f is not equal to null, I'll keep reading. Remember that fgetS returns null if we get to the end of the file. Okay. For now, I'm just going to print this line, but we're going to do more interesting things later. But that's what I'll do. I'll close the file, and I'll return exit success. Whoops, sorry. Okay, so hopefully nothing weird here. This is what I said we'll build on. I'm reading one line at a time in the file. I'm printing it to screen. What I want to do now is instead of just printing, I'm going to store the contents of the file so I can do things with it. If I was using array at this point, I would have to go through the file twice because I don't know how many lines I have. What I'll do is, in that case, I'll probably increment a counter every time I read a line. And when I finish to the end of the file, I'll rewind the file to the beginning again, allocate the memory I need in the array, because now I know how big the array needs to be, and then I'll do the same while loop again. That's wasteful. It's okay, of course, because computers are fast. But here's another reason why having something that's dynamically resizable would be a good thing. So how do we do that then? I can compile this first. I don't know if you finished writing, but let's see. And we will convince ourselves that it's working. I'll let you finish the writing if you need it. If you look at the programming assignment for this week, PA7, there's example code that does basically this. But also, after you finish reading the file, it will call merge sort, the code that you're responsible for building. And Professor Lu will talk more about these details on Thursday. So let's see. Let's just pass the file. It's our source code itself, and it does what we expect it to do. It prints every line of the file. So nothing really surprising here. Now I'm going to implement linked lists, and the way we implement linked lists obviously is that this is something that the programming language does not support directly. It's not built in. It supports it, but it's not built in. So obviously we're going to have to define our own data structure to do this. And if you remember from what we talked about a couple of, I think it might have been 2 weeks ago, we talked about structures. That's one of our learning outcomes. So let me decipher this to some degree here. We're going to need a data structure that can capture these guys right here. Something that has a payload and a next pointer. And I'm going to call it struct. I'm going to I'll use the struct keyword to generate a new data type. And this is what I'll call it. Each list node is going to be called list_t. So this is a convention in C programming. If you see a name and _t, it just means type. It means that this is a data type. It's not a function. It's something that programmers do to communicate with themselves, because maybe I'm looking at code I haven't seen in months, or with other people who are looking at my code. The payload for an editor are not numbers, they're strings. Right? That's what we said before. So my payload is going to be this. Of course, you can call it whatever you like, and in fact, it might be better to just call it a line, but it really is the payload. And then I needed a next pointer. And here is a point of confusion often, because the next pointer needs to refer to something of the same type as the objects themselves, as the list nodes themselves. So in other words, what I need to do is this. Okay. This looks confusing because, how can I use the function, the data type itself inside the definition of the function? So yes, the problem here, I shouldn't say problem, the observation here is that this is sort of a recursive data structure. You've seen recursive functions. This is kind of, not really, kind of a recursive data structure. The difference is we're not saying that inside a list node is another list node. We are not saying this, because if we did that, well, of course, inside that list node, we would get another list node, and so on forever. What we are saying is that inside a list node, there's an address to another list node. That's a significant difference. It means that the compiler says, okay, I know that list T is a structure. I'm actually looking at it right now. And what you want to include in this structure is a pointer. And I know what pointers are. I know pointers are the size of the memory structure of the machine we're running on. So that's no problem. If I had tried to do this, everything would blow up. Because the compiler, I would be saying that a list node contains a next pointer, which contains a list node, which contains a next pointer, which contains a list node, ad infinitum. We can't do that. So this is the right syntax here. Okay, so far so good. The only problem we have remaining is a minor one, but I don't know how much Professor Lu has told you about C programmers. I'm a hardcore C programmer, which means I'm lazy. Hopefully you'll get lazy too. So every time I see something like this, it says struct list T, and in fact I see this too, struct list T, my lazy bone kicks in. I don't want to have to write struct, because it's a waste of typing. I just want to be able to use the type without having to put struct in front of it. You've seen this before, I'm sure. You've seen type defs. Type defs help you save some typing. You say, so a type def really, draw it here. A type def has this format. You say, here's the keyword type def. Here's a type. It could be long. I want to call it by this alias from this point on in the program. So if we would apply this here, I would say type def, the type, that's the structure definition I used to have. Struct list T, char line, struct list T next. And then the alias would come here. I show you this partly because it does save you some time typing, but partly also because C programmers do this all the time. It's an idiom. You see a type set, you have a struct, list T, usually list underscore T, and then you have the type itself without the underscore. You'll see this in the programming assignment too. I don't want you to be confused if you see it. One minor thing is, it's a minor thing. Again, I want you to see it and understand it. You would think this would work. Don't write this. I'm just trying to illustrate the point here. You would think this would work. So that I don't have to even write struct list underscore T inside the definition. But it does not. The reason is, at this point in time, we haven't finished the type definition, so the compiler does not know what a list without underscore T is. That's only after it's finished this particular line. So I can't use the shorthand inside the definition of the structure. So if I can't use the shorthand, I have to use the full name. And if I want another, that means also that I have to give a full name. Maybe this gets a little confusing, but basically, a type definition, the type itself that I'm passing here does not have to have a name. It could be, yes, type def struct, and that this is known as an anonymous struct. Something like this. And what comes between this curly brace and that particular keyword is a type. It's anonymous. It does not have a name. We didn't call it anything. The type def says whatever this anonymous struct is doing, we're going to call it value. But for the argument I said before, if I want to refer to myself, if I want to refer to the line T type, it needs to have a name. these are not extremely important notes. I'm just trying to stave off any confusion when you look at C code in the future, and so that you understand why we do this. Okay, so I've defined my structure. I have payloads of strings. I have an X pointer. Now, we sort of want to build the library, the set of functions that deal with linked lists. Because when I'm writing my main function, I don't want to have to deal with all the details of creating a new list node, inserting it, removing it, deleting the list, and all that. Instead, I want to create nice little self-contained functions that do those jobs for me. And as an example, to give you a guideline for what I'm talking about, think of this guy right here. Think of this data type. You've used it several times. You probably never thought about it. But of course, this, the file record, is a structure that's defined in the C standard library. We never have to open and look at the contents of that file structure because the C standard library provides all the functions that operate on this. We have fopen to open files and do all the work that involves. We have fclose that takes the file record and closes the file. We have operations like fgetS, fputC, fgetC, and so on. This is my message here. Just like the file record has a bunch of functions that do all the work that we call without having to worry about how they're implemented. That's what we're going to do with the linked list. We're going to create a bunch of functions that take care of creating a list, deleting a list, inserting nodes, and all that. So that whoever's using this, the main function right here, or someone else doesn't have to know all those details. So I'm going to start populating this and creating a bunch of these functions. And my convention is it's going to be that every function that deals with the line data type will have line underscore as a prefix. So, for example, given a string I've read from a file, I'm going to create a new line. And the return value of this is going to be line pointer. This is typically in object-oriented programming known as a constructor. So if you're going to do object-oriented programming later on, or if you're doing it already in other programming languages, this is what you're looking at. A function that constructs a particular data structure and populates it properly and initializes anything properly. So how would I do this? Well, I have to create a line. I would call malloc, because it's a dynamic data structure, right? So, and I'm creating things of the size of the type line. Then I want to populate this. I want to initialize this. The very first thing is that I want to take care of the payload. Remember, the arrow notation is what we use for accessing the contents of structures when we have a pointer to them, which is really the same thing as dereferencing the pointer and then putting a dot. So we don't have to write that one, but this is the same meaning. So I'm going to fill the line. And what I'll do is just copy the string that I'm getting as input argument here. The reason being, if you remember down in the main file, I had a single buffer I was using and reusing over and over again to read every line. So the understanding here is that the data, the string you're getting is just something you borrow. You can't take it. Because the next time I read another line, that content's going to change. Yes?
So when you said in the previous function, you said type def struct list t, and then you have the list at the end.
Yep.
When you call list, like when you use the word list, what is stored in it? Like,
What's what that's stored, what does it mean?
like when you say typedef struct
Yep, yep.
something, the whole function, and then list in the end of it.
Mhm.
So your list is the name of,
So what I'm saying is, this type, which I have highlighted,
right,
please allow me to use this alias instead of this whole harangue. So that's list. The list at the end of the line there is the alias I want to use because I think it's nice and clean. It stands in for the entire highlighted thing. Does that make sense? So it's just, you know, I don't have to use typedefs.
right.
I do it because I want to cut down on some typing.
It's,
It just means that I'm creating a type, it's called list T. An alias for list T, well, an alias for struct list T is list. That's all that means. That allows me to write this right here. I'm sorry, what's that?
is that supposed to be list and then?
On this line, yes. Where? Oh, I'm sorry.
Okay.
Okay, so I'm blind up here coding. I apologize. How should I fix this? So this is the thing. I wanted to use line because this is a text editor. Sorry about this. And but the programming assignment uses a type that's called list. Thank you for noticing that. Thank you. I apologize. Okay, so
Do you still have to like?
yes, I do. Thank you. This is the thing when you program in front of the crowd. Okay, does this look good to everyone? I should have said that I wanted to test you. I missed that. So, every time I create a new list, I want to make sure, a new element, I want to make sure that it doesn't point to anything. Because if it doesn't point to anything, it's the end of the list. If it points to some random variable, well, then we have some type of undefined list where we don't know where it ends. So, creating a node, the very first thing after I filled in the payload is to set the next pointer to null. That's what I'm doing here. This, if you think about it, is a list. A single list node is a list. It just contains one element. And in fact, a null pointer, a head pointer that doesn't point anywhere is also a list. It contains 0 elements. Okay, and then finally I'll return the node. Okay, any thoughts or questions here? Any other mistakes? So this is sort of our F open, if we think of file terms. We want an F close, or really a function that takes a list node and gets rid of everything associated with it. Okay. And that's, so I said before, in C programmer, in C++ or Java or other object orientation terminology, this is a constructor. And what we're doing now is a destructor. Okay, so our destructor, of course, is going to be called line, and I'll call it destroy. That's a common name for this type of thing. And it will take a node. Oops. So I'm destroying a single node. This is important because later on we're going to be destroying an entire list. So these are going to be slightly different. I will just, first, if I have allocated some memory for myself using str., which you remember has a malloc inside, I have to free that memory. And then I should free the node itself. Obviously the order here is significant, because if I swap the order, I would first deallocate the memory of the node, and then I would access the contents of that memory to free the line. That would get you a segmentation fault. Most often. It's illegal to do this. Valgrind will complain. And your code will likely crash at one point or the other. Okay. So these are the easy ones. Let's think about inserting now. let's think about me having a list. Let's say it's a simple one. And I want to insert something at the front. So I have a head that points to the beginning of the list, and I want to insert, let's say, 7. Insert front is what we're going to call this. How would I do this? How would I insert anything in the front of the linked list? Any thoughts? It's not that hard. What will be the new head, first of all? Will the head change? Yes, the head will change. Great. What will be the new head? This one, exactly. So what I have to do is say head used to be pointing at 19, it's going to now point at 7. What else happens?
You have to move the null pointer to point to the node that's linking.
Exactly. Because if I don't do that, I lose the entire list. I have to remember to link in a new element that becomes part of the list. So let's do this one. I'm going to call it line insert from. And I will take 2 arguments, the head and the node I'm inserting. Now, there's a small design issue here that people who build linked lists are sort of divided on. Some create what's known as a sentinel element, which is a single element that does not contain anything, that keeps track of the head and the tail sometimes, but at least the head. That allows you to easily add and remove elements without having to write special code for this. In this particular case, I'm going to do the other approach, which is to say, if I want to update the head, which happens commonly, I will create all my functions that potentially update the head to have a return value that is the new head. Let me show you what I mean. What I'll do is this. Essentially, I'll say, okay, node next. The element I'm inserting into my list, in this case the 7, its next pointer should point at the old head. Right? That's how I link it in. And then I'll return node. The convention, as I said, was that whatever's being returned from these functions will be the new head. That just means that whenever I call this function, I have to assign head to the return value of every time I call this function. So that's how simple this is, inserting at the front. Let me scroll down to show you how I would change this. Instead of printing, what we're going to do is we're going to create a list, and it will start out being empty. So it will be an empty list. It will have a null value as the head. And then what I'll do is just say the head is now going to be return value of insert front of the head. This is the old head. Plus, and calling this on line create on the buffer. So see what I'm doing here. I'm calling line create, the constructor, passing in the string that I was reading from the file as its only argument. This will create that node and return it. The return value of that will go in as the second argument of the insert front, which I insert into the head, updating the head every time I go. Does anyone have any predictions what will happen in terms of the output here? I'm inserting things, I'm reading lines, one at a time, and inserting them in the front of a list. We'll figure it out. I think the one thing we want to do, of course, is to print. So I'm going to print the list, and I will then destroy the list. Because you have to remember to clean things up afterwards. I have to write these two functions still, so we'll go up and do that. Okay, so see, I said line print. And then line destroy list.
You already made that.
What's that? I will fill in the code if that's what you mean, or no? Did someone say anything? So, both printing and destroying the entire list is known as a traversal. Remember that we don't have random access, so we have to sequentially visit every node. We call that traversing the list, or a traversal of the list. Starting at the head, we'll go through each of them and do whatever we want to do. In this case, printing each element and then go to the next. Or, for the next one, destroying the elements, go to the next, or whatever. There are two ways to implement this. One way is to do an iterative solution with a for loop or a while loop or things like that, which is often the fastest way to do things because it doesn't require you to call, change the call stack and all that. But the recursive solutions are often more elegant, so we're going to talk about those here. Any thoughts of how I could implement this recursively? If there's some time at the end, I'm going to talk about the iterative solutions too. But I want to print the list. It looks like this. How would I print that recursively? Any thoughts? Remember that for every recursive function, we have two cases. We have a base case that tells us when to stop, and then we have an inductive case that says if we're not stopping, this is what we're doing. Recursive case. What might be the base case here?
When the pointer is small.
Exactly. If that is equal to null, I will just return, I'm done. There's nothing more to do. The recursive case is print and move to next. How would I achieve that? Well, the printing part is easy, right? We did that already. Printf head. What's it called? Line? Yeah. How do I move to the next? It's recursive, which means I will call myself. So, line print. How would I print the next thing down the line? No, it's early, but it's not that hard. Easy, right? I visit myself. And along the way, of course, we're going to come across null. If that happens, our base case will trigger with return. So you get this cascade of return. What about destroy list? It's also traversal, I said. We can do it recursively. We can do it. We can do it recursively or iteratively. I'm going to do it recursively. The base case is the same, right? If I reach the end of the line, there's nothing more to do. I'll just return. The recursive one is slightly different. Why is it different? I mean, I could, you know, it's very similar because I have to essentially, instead of printing, I'll delete something. but then I'll move on to the next. But there's a difference here. Does anyone spot the difference?
If you freeze the list, we use the next pointer.
Exactly. So what does that tell you? You can't free this node, because if I do, I lose the next pointer. So that, in other words, I can't do the exact order. I first need to destroy whatever comes downstream. I can destroy what's downstream. Then I can destroy myself. I can't do it the other way. Exactly like I said before, if you had in the destroy, if I scroll up quickly here, I'll show you. This one, I have to destroy whatever is contained inside the node before I destroy the node itself. Otherwise, I'd be sawing off the branch I'm sitting on. Okay, so destroy and destroy myself. So now I'm calling this function I just scrolled up to, the destructor for a single node. It doesn't destroy an entire list, it destroys one of the nodes. So the meaning here is that I first visit everything that comes after me. On the way back, because somewhere along the line we'll reach the end of the list, we'll get a null, we'll return. That function that called destroy list on the end of the list, we'll get back, we'll destroy that last element. Return, restore the last element, and so on. Yes?
When I do this, I create a pre-pointer function next, I feel
Yeah, so that's, well, you can do that too. Exactly, you can store the next value. So you could do, the observation would be this. You don't have to change this. I think this is, in my mind, it's slightly more elegant to do it this way. But what I could be doing is to say, line temp is called head next, and then I would line on the end. If nothing else, one more line of code. That's significant, but definitely a good solution. Okay. So I think I have enough to compile this. Let's see if it works. Oops. Yep. People are nodding. Why are you surprised here? Or is anyone surprised? Well, I'm doing sort of the same thing, but of course, the order has been reversed. Why is that? Why has the order been reversed? Well, obviously, I'm reading from the top of a list to the end. Everything I'm inserting at the front of the list. So that means I reverse the order. What I really should be doing is I should read one line, and I should insert at the end of the list. So to do that, we're going to have to create a function called insert back. To fix that part. And insert back is a little, I shouldn't say, well, it's a little trickier. It's still not a big deal, because we already are masters of traversals by this time. So let's look at it. Insert back. We'll have the same look as the other. But now we're going to have to traverse. If the old one, insert front, we have to put it front and return to head, that was fine. There's no need for any recursion. In this case, we're going to have to traverse until we reach the end of the list. That's where we insert. How would we do that then? Well, it's recursive, so let's start with base case. Any ideas? Yes? Well, you said when...
Head of next.
Yes, Well, you're assuming, you're assuming that you're not getting an empty list, but you might get null here. You might be trying to insert at the back of an empty list, which is fine, should be fine. So I can't, if I do this, I assume that head is not null, because otherwise I'll get a segmentation fault. So I'm actually going to short circuit this a little and say, if head is equal to null, that's when I want to stop. If head is equal to null, well, what should be the new head? Obviously no. Right? I'm inserting a node into an empty list. That empty list, I reach the end of the line because there's nothing else after null. So the new head will be node. And in fact, I realize I should add this too. As a precaution, I will also say that node next will be null. In other words, I will ensure that I don't know if the node I'm getting past if the value its next pointer will be. I know that after I've inserted it at the end, it should have a null here. So that's what I'm ensuring that is true on this line right there. And then I say, as you remember, the convention for all my functions would be they return the new head as the return value. So that's what I'll do. So recursive case, not at the end, move to the next. So to do that, we're going to have to recursively call. There's no work to be done here. We're just going to keep going. So to do that, we're going to say, well, head next, whatever comes next, is going to be the return value of insert back. We're passing head next and node. We know that this node is not going right where we are. It's going to come down the line. Any questions? Yes?
If you have
I have to return head. Yep.
if you have a list which is one element, like let's say it's just 19 and then
Mm-hmm.
So obviously you wouldn't trigger the first case.
Yep, it wouldn't trigger the first case. Mm-hmm. So what I would be doing, so let's go through that example. It's a good question. So I'm inserting, we already, I think, convinced ourselves if our list is empty, we will trigger the first case, and our list will now be the node we're inserting, so that's good. What about our list is 19 and nothing else? And I'm inserting, let's say, 14 here. Yeah. So the first time around, 19 is, well, head is not null. So the recursive case is that, okay, we're now going to update the next pointer. The next pointer, which is going to be replaced with whatever is returned from visiting the next pointer with the node. So we're going to come back recursively. This time, we're visiting null. So of course the first case will be trigger. The first line of the base case is to say that this will be null. I'm ensuring this is null. And then I'll return node. Back to the recursive call. That one said head next will be assigned to whatever was returned. In other words, this head next is replaced with a pointer there. And then this last line of the function here, right here, the observation is that we were not inserting anything at this location. This is not the end of the line. That's why we came here. If this is not the end of the line, the head will not change. So I'll just return the old head back to whoever called it. Does that make sense? Okay, so let's compile this. Do I just close that? see. And as you see now, because I was inserting at the back instead of the front, things are better. Things are in the right order. Okay, so we have about 13 minutes. Any questions first of all? My plan was to look at some of the iterative solutions on linked lists now, instead of the recursive ones. So the recursive ones are elegant, but if you have a very long list, visiting every element using a recursive call, you're going to induce a fair amount of memory on the call stack, sometimes to the point where you run out of the stack space. So it always makes sense to implement these things iteratively too, just also so that you've seen the code. So let's start with something simple. Let's do line print. Call it iter, like that. And the task is just to traverse a list using a while loop, or for whatever we need to do. We don't have to worry about base cases, but we do have to worry about when do we terminate, when do we stop. And in this particular case, it's really simple. It's basically the same thing. So I'm going to keep recursing, iterating, looping, while the head pointer is not null. And every time I come across the head pointer, a new loop, iteration in the loop, I'll just print that line, and then move on. And moving on is easy. I update the head pointer to be next. You see this very often. You might get dismayed when you see this because it sort of looks like I'm trashing my list. Right? I get a head, and every time I update the heads, I sort of throw away the elements before it. But remember that the C language has call by value. So the pointer I'm getting as an argument to this function is a copy. I can do whatever I want with it. When I leave the function, all is forgotten. So I will not trash the list when I do this. So I can just print this iteratively instead. Compile it. In this particular case, with such a small list, there's no big difference in performance. It seems the same thing, that works the same way. But for very large lists, let's say you're managing some type of database system where you have a lot of data in memory, it will make a difference. So the iterative solutions are often not as elegant. They're often more lines of code. In this case, it was not. There's no real difference. But they are faster. So insert front is the same. This is not a recursive function anyway, so I don't have to do it. I don't have to change it. But what about line insert back? And it's called it. So I don't want to see any recursive calls here. That's the basic idea. And the first thing I'll do is just, I did that before too. I want to ensure that the element I'm inserting has a next pointer set to null. But when we had base cases for the recursive function, we will have special cases here. We have to figure out the special cases that we have to treat differently than anyone else. And there's one special case here. What might that be? The problem is this. We got away with this problem in the recursive solution because we said the return value of the function is going to be the new head. So that was easy. We had no issue with it. We could come across it. But the issue we have here when we're doing this iteratively is that if we ever get to a point where we reach reach the end of the line, let's say, we read the value of the next pointer, and it is null. We need to have remembered the previous element. You know, the null pointer, it basically points to nothing, right? So if I got to this point, I need to have remembered the previous element in order to update this, what this would be, to the new element I was inserting. So I sort of have to look ahead one step. I can't look at what head is pointing to, because if I'm looking at what head is pointing to and head is pointing to null, I'm done for, because I can't go back to the previous element. There's no backwards link in a linked list. In a single linked list, double linked list, you do have previous pointers. But at least you don't have single previous pointers. So if I would do something like my print iter function here, where I'm just checking to make sure that head is not null, and then move on to the next here. Well, if I get to the point where head is null, the game is up. I've lost the previous pointer where that new element is supposed to be inserted. So this actually means that there is a special case that I have to treat differently, and that's when the list is null. The list is empty. If the list is empty, which I know if that is equal to null, I will just return the null. Having taken care of that step, it's easy. Find the end. So what I'm going to do is I'm going to create a little cursor. Remember that at the end of this function, I'm going to have to return wherever the head was. So I can't trash the head. I could do that when I was printing, and I didn't return anything. This time I need to save my head, my old head. So I'm going to create a little temporary variable that I call cursor that I'll let slide along the list until I reach the end. And as I said, I have to look ahead now. I have to, I can't just see whether the cursor is null, I have to see whether the next cursor is null. And this is the comment we had before in the front. We look at next instead of the cursor itself. If the next cursor is not null, we should move on one more step. If it is null, that means this is the place we're inserting the element. But in this case, we know that it's not, so I just update this. And when this while loop has finished, you can all agree that we have reached the last element. You know that the last element, which has a next pointer of null, is now contained inside the cursor. That's where we need to link in the element. So that's what I'll do. Cursor, next, we know it's null, it's now going to be node. And then we return the head. Any questions here? Yes, in the back.
Don't we update head later? Like, head hasn't changed.
What's that? Do you? I'm not, I don't want to update the head because I already eliminated the case when the head is changing. Is that what you're asking? That's the special case. If there was an empty list, that's the only time I will change the head. Okay? So then, otherwise, it's not an empty list. The element I'm inserting will come somewhere down the line. It will not be the first element. And let's see, I can change the code to use this too.
So if it's not an empty list, you're returning totally unchanged head.
Yes, exactly. So if it's not an empty, yeah, exactly. So that the head will not change. Some other element might change. So, and it might even be that the head's next pointer might change. But the element, the piece of memory that we call head is not going to change. That's the meaning. So did I read Okay, still seems to work. What else could be interesting to do? So, I mean, I think I don't have to talk about an iterative version of destroying the list. It's going to be very similar to printing. You just have a traversal where you go to the end and you destroy everything. So that's not a big deal. Maybe something that might be useful is, and I have 3 minutes, I don't know if I can do it. Maybe it's more of an exercise for you guys to think about it, not to, I don't think it's part of the assignment. But it's useful as an exercise to yourself. What if I had a function, and actually it's supposed to return line. This question has come up many times on exams. That's why I bring it up now. Consider this fair warning. What you want to do is, given a linked list, let's say this one, 42, 7, 13, 17, 99. Reverse the list. Give me a new list that starts at 99, 17, 13, 7, 42, without allocating any new memory. Yes?
Can you not just use the front, insert front?
Yes, but if you said that in the exam,
Well,
in this case you could, yes,
Yeah.
absolutely. You could organize the way you insert things, so you insert front instead of insert back. But let's say that, the merge sort that the programming assignment is on, you run merge sort, and then you want it to be descending instead of ascending order, so you want to reverse the list. So you had something that was sorted to increase values, but you wanted to get out of the way. So you would have a function like this that reverses the list. So this is very common to need to be done. The challenge is, how do you implement this without copying every element and inserting it into a new list? What you really want to do is just essentially swap the pointers. So this should be my head, and the next of this one should not be null, but 17, and the next of this one should now be, let's see, 13. This should be 7, 42, and this one should get a null here. It's actually not too tricky, but think about this, look at the exams. Remember, the next midterm is already next week. And maybe you can surprise Professor Lu with asking him how about to do this too. Any questions? Okay, so hopefully he's back on Thursday. Otherwise, you'll have me again. But thanks everyone. I'll see you at the exam.